Welcome to All the Best, an interview series with UNL Orca awardees, where UNL means University of Nebraska-Lincoln, and Orca is the Outstanding Research and Creativities Award, which is UNL's top award. In Gerda Lerner's book, Why History Matters, she explains the life stories give meaning to the present and the future because we identify what is important to us. And she says, our stories show how we are interconnected in a particular time and place. As for this interview series, Orca awardees have experiences that reach back more than a half a century, which will give us a personal view of how the best research emerged from UNL. It is my pleasure to introduce today's interviewee, Dr. Xiao Cheng Zeng. Xiao became a chemistry professor at the University of Nebraska-Lincoln in 1993, quickly rose through the ranks, and was in the department for 29 years. In 2022, he left to become the head of the Department of Materials Science and Engineering at the City University of Hong Kong. Xiao was born in Beijing and earned a bachelor's in physics at the University of Beijing in 1984. Next, he traveled 6,800 miles east to Ohio State University in Columbus, where he earned his doctorate in condensed matter physics. He followed that up with two postdoctoral experiences, first at the University of Chicago, and the second at the University of California, Los Angeles. At UNL, Xiao's lab carried out theoretical/computational studies on a wide range of interesting solids, liquids, and gases. In 2010, he received the Outstanding Research and Creative Activities Award, which is the University of Nebraska System's highest honor. With that, I want to welcome Xiao to the interview.
Oh, thank you, Mark.
Yeah.
It's been a while to see you, but you look good, Mark.
Thank you. So what I like to do is start out by asking, what did you see or what did you experience when you came to the campus for the first time? What are your thoughts about it?
Oh, yeah. Actually, I came from, as you said, I graduated from Ohio State. I find a university very similar to Ohio State.
Okay, yeah.
That's my first impression. But the most impressive thing is the building of chemistry. And in Ohio State, our building is about fourth floor building. And UCLA chemistry department also fourth floor. And our building is seventh floor. Wow. And maybe one of the second tallest building on campus. And it's the only one building devoted to the chemistry. So I thought this department was great. Yes. So that's a very good impression.
That is a good impression, yeah. And Ohio State is really big, right? Probably even bigger.
It's big.
Really
but
big.
Our building is just has four floors, so it's smaller. And it's big. It's a slightly bigger department, but yeah, so that's why Nebraska chemistry was so special at the time.
Yeah. All right, let's jump right into your research, your ORCA research, and give us a sense of why you think you won it, and then what did you do, and why is it important?
Yeah, I show you some slides here, although your audience may not see that. Yeah. So if you see my top three, I would say my top discovery in Nebraska at UNL, one is this Bucky gold, the first cage molecule of gold we discovered, and that's one. And the second one, so that one actually, if you look at this slides, it was highlighted by New York Times. You know, yeah, this is New York Times, and it was also featured on the cover of PNAS. Yeah. So I have about 700 paper or so. This is the only paper, got a phone call from New York Times, and they wrote a special feature story. The title is 16 Gold Atoms in Search for Catchy Names. we didn't get you can look at this cover on PNS. We just simply call it hollow gold nanocages. Yeah. We thought about some fancy name, but in the end we just make it simple that people to understand. But why it's important? But if you look at the left side is buckyball C60. That's the first cage molecules discovered by a human being. And three people who discovered these received the Nobel Prize. They are viewed as the father of nanoscience. Yeah. So and our work is complement to that. Theirs is the like insulator cage, right? Carbon. Ours is a metal cage. So that was received. Why it was received this feature story by the New York Times. So that's one. And the second one you probably know a lot. That was the Nebraska ice.
Yes.
Okay. So Nebraska ice was looking like this. This is a two-layer, like two graphene layer on top of each other. But we discovered when I was assistant professor, yes, and so that was made a name. It was published my first paper to Nature in year 2000, and most why it's called the Nebraska ice, because my colleague, perhaps it's either Eckhart or George Sturgeon, told me Nebraska has a special meaning. It means flat water. It's an Alto-Indian word.
Yeah.
And if you look at the map, I've shown this map too when I give a speech worldwide. A lot of Midwest states name associated with water. Yeah, like Michigan, Minnesota, Ohio. These are all different Indian words. So that's why we name it. We give a nickname Nebraska ice. And then that ice was confirmed by two experiments, and one was by DOE. National Lab at the PNL, and another experiment was done by Beijing University in 2020. So it has two experimental confirmation. So it has an official name now. It's called the two-dimensional ice one. So that's the one. Yeah. The three-dimensional ice one is the one you use in. Yeah, if you grab the ice in your water, your glass water, that's the three-dimensional ice. So Nebraska is. Official name is two-dimensional ice one. So that's important one. And the third one is the ice nanotube. I can show you this ice nanotube. Yeah, it's this is the ice nanotube. That's this is it didn't show the movie, but that's okay. It formed, we predict it formed inside carbon nanotube. When you, it's just like experiment you would do. You put a glass of water in your freezer, and then every half an hour you observe what happened, and then eventually you see the water will freeze into ice. And this is the same thing. But we observed in computer at the time. So these are the my top three discoveries in Nebraska, and so this is my second paper to Nature. And so this is, and so I was after this paper in 2002, I was promoted to the Wheeler Cather professor, named the professor. I'm class number one. Maybe I was the youngest one in that class. Yeah, 2002. So that's about 9 years after I joined the university. Yeah, so that's why, because this kind of fundamental discovery, university really value these fundamental. Yeah.
Very exciting. I remember all of those discoveries.
Yeah, and you saw I gave you a video. Actually, university made a video.
Yeah.
Do you have time? Yeah. So they mentioned some of these.
I could put a link to it.
Oh, okay. You did. Yeah. So Pat gave a, he was the chair at the time. He gave a lot of. If you look at the video, it gave a lot of, introduction of my work at the time.
Mm-hmm. Great. So tell us, well, I was curious, the gold cages,
yeah,
they also confirmed to exist?
Yes. This one was lucky. Let me go back to that picture. Yeah, this one was lucky because you can see their co-author is a Wang. Yeah, he was at PNL National Lab. So we discovered from computer simulation there's a cage molecule at 16, but we thought we made a mistake because The reason is the gold, all the metals, so far people find small clusters are compact because the delocalized electron. So there are no, people imagine you would have a cage molecule.
Yeah.
And so that's really, so we hesitate to publish. So I showed a experimental group, and I listened to Professor Wang's talk. He studies small gold cluster, and they have some data actually, of 16, but they don't know what structure, because the published structure on the market, none of them fit. Okay.
Oh.
And so I said, I have a new structure never saw before. It's a cage. And then he gave me this so-called fingerprint data. It's very valuable experiment data he gave me. And I calculate the spectra, so-called photoelectron spectra of this cage, and it matched perfectly.
Wow.
Matched perfectly.
Wow.
Yeah, if you are interested, I can show you another slide. This one I just prepared for in the interview.
Yeah.
I didn't go into detail, but it shows it's a fingerprint. It match finger by finger, and so that's how it worked. Because at the time, 20 years ago or 25 years ago, it's too small to see this kind of 1 nanometer, sub-nanometer structure.
Yeah.
And so, but the spectroscopy, we can calculate. He can measure. So, and then we can match. It's not IR, but it looks sort of like IR. You can match, and then you know the structure. So that's why it was discovered by experimental team and the theoretical team together. Yeah. It was a very good story. So DOE also has a featured story, and Washington, Seattle has a newspaper also highlight, and Omaha also has Omaha newspaper and the Lincoln newspaper all highlight. There were 40 media worldwide talk about this work. Wow. I have those. Yeah, I only highlight the New York Times.
Sure.
But it's real printing, not online. I still have some hard copy. Some of them still in Hamilton Hall. They're still there. Yeah. It's an old time. People, read hard copy newspaper. Yeah.
Yeah. So let's talk about some of your students and postdocs. I know you had a lot of postdocs, but
yes.
Could you tell me about some of your early graduate students and how they came to be in your lab and what did they do?
Yeah, this is the first picture of my group, maybe 2 or 3 years after maybe 3 years after I joined UNL. Yeah, then here's me. And this is the first postdoc, the Koga, he's from Japan. Oh. He was my first postdoc. And now he's a professor in Japan, University of Okayama. Yeah, and he's the one. My first two students, Kwon Jin-oh is a Korean student. He's my first PhD student. Here, you can see my mouse cursor, right?
Yes.
Yeah, he's the one. And after graduation, he went back to Korea. Now he is working in the supercomputing center in South Korea. And this is my maybe second graduate student, Ruben Para. And he's originally from Colombia. And now he is a chemistry professor at DePaul University in Chicago. Yeah. And I think he become a associate vice chancellor for some kind of outreach, or because he's from South America. So so he is that. And this may be my third student originally from Russia, Baikov. Yeah. And now he's working in Texas in a small liberal arts school near, I think near Dallas. He's a department chair in that small liberal arts school. Maybe, I forgot the name. Murray? Yeah, Murray University. Okay. Yeah. So these are some of my student postdoc, and then this is the second postdoc. He is working now in U.S. in the this Guangtu Gao. He's working in this agriculture lab near in Virginia. Yeah, some kind of Department of Agriculture. Yeah.
So very international.
Yeah, very international. These are hired. So Kwon of South Korea was interested by Peel. He was Peel. Yeah, he's a chair. And this Japan was due to my first NSF grant.
Oh.
Yeah, you will ask that question, but I can answer right now. That's my very first grant, international grant, allow me to visit Japan. And so during that 1 month I stayed in Japan, I recruited this first postdoc. And this Chinese postdoc is also a grant from NSF. At that time, they support my trip to China. So that's 95. So I visit China, Beijing University of Chemical Technology, and recruited this postdoc. And so both these postdocs were the first author or second author of that Nature article, first one. So yeah, it's a very international. Colombia, South Korea, Russia, Japan. So these are my first group photo, and but then I had I can show you some of the later, and this is 10 years later my group photo. Also Japan, many international, and I'll show you here 2020 Uranium. This is in Pioneer Park or Holmes Lake. Yeah, these. Yeah, so I prepared to show you some of the history. 2011 getting bigger. Some they have kids. This is 2015. Yeah, 2015. This is 2016. This is big reunion 2016. They come from all over the world. 2018 and 19. These are, and then 2020 is pandemic, and then everybody stayed. Yeah, so you can see the history of these my group evolving from the very international. Yeah.
And so everybody in your lab got a computer? Is that how it worked? Or did they have to share computers?
Yes. I have a photo of computer here. The big computer is called Prior Fire. Let me see. I may have it. Let me see. Oh, okay. I see. I don't have that. So I also purchased some computer for my group, still in the basement of Hamilton Home. But university has a big computer. First one called Prior Fire, and the manager director of that computer was my former postdoc. But he passed away. Called David Swanson. I don't know. You remember this name?
No, I remember Dave. Yeah.
Dave. Okay. Yeah, he
really nice guy.
Very nice guy. He was a PhD of cricket card, and then he briefly did a postdoc with me and went to Navy for a postdoc. And then once the university got this big grant, AppScore grant, we want to build a big computer cluster. So I called Dave. He was in Navy at the time, and he said he want to come back home, and then become the director. And he worked as the director since then for maybe 15 years before the accident. He had very tragic accident in the car accident.
Yeah.
But he would be still director if he worked. Yeah.
No, I remember all those computers that you had.
Yeah, very helpful. He also managed them, and he grew the computer bigger and bigger. Yes. So I think the university still have that. It doesn't call, I think it changed name for something else.
Yeah.
Maybe Fire. Yeah, Prior Fire. Yeah, some other name. Yeah.
Okay. Let's go back here. In the area of computational chemistry, how do you define impact? And one thing that I'm going to do, I'm going to show you how many citations, some papers that have very high citation numbers. But when we are hiring people who don't have a large publication record, how do we know they're going to be successful? So how do we define, or how do we choose people who we think are going to have an impact? Just give me your thoughts on how you choose new faculty.
Oh, for me, so in Hong Kong, it's we want to see some track record.
Okay.
So people need to have perhaps longer postdoc time.
Okay.
Because competition here is higher. We hire from worldwide people. So yeah, it's like if you don't have track record, then we have that kind of certainly we could interview one without many publication. We interview deeply and spend more time and ask him or her ideas and what he want to do. And but you also have the question whether he or she said a lot, whether they can deliver, you know. But if they had some kind of a publication, they don't need one. We only need one representative big paper, you know, either JAX or PNAS, one paper, and tell me how they, you know, accomplish those. Like I just told you, where the idea, and then this kind of string of thought of making a big story, one good paper. You know, they don't need many, you know, small paper. They just need a few, but one very big one. So that's how I come up with the interview and tell me that story. Okay. You know, just sort of like your interview. I interview this candidate and see, and so people interview, see how he responds, how he creative thinking, where that chain of thought lead to that big paper. Yeah. Mm-hmm. That's how I manage the this, you know, as the head, how I recruit people.
Okay, so then if you could stop sharing, I'll share with you the slide that I've got with your highest cited papers.
Okay. And that carbon nanotube one is very high.
Yeah.
Yeah.
So on the Web of Science, and there's a number of places, of course, that we track stuff, but on Web of Science, which limits the number of citations, it's lower than most places.
Right.
I found 3 papers that were pretty much over 1,000 citations.
Right.
And I tell every interviewee that, in my opinion, if you've got more than 50 citations, that's a large number, and these are over 1,000. And so I wonder if you could just tell us about some of these. We'll go to the bottom one, which has...
The third one is why it's important, because it's a pure theoretical paper, computational.
And let me read the title. Formation of ordered ice nanotubes
inside carbon nanotubes. Yeah, that's the one. The first author was my first postdoc, Koga. He became a Japan, you know, professor in Japan. Yeah. The other 2 are good, but they are largely done by experimental group. Our role is supporting them to explain the phenomenon they discovered in the lab.
Okay.
So it's a joint paper, largely. So experimental paper tended, especially hot experimental work, tend to get more citations.
Sure.
Whereas theoretical paper is much harder. So that's the third one, even though it's number 3, but I view it as a pure theoretical one. That's my best one. That's one of the top 3 I showed you. Okay. And then the gold one, and also the Nebraska ice. Nebraska ice citation also, pretty good, 400 or 500-ish, pretty good. And gold one maybe 600-ish. So those are pure theoretical one. But I did collaborate with a lot of experimental group and worldwide. The first one was professor in mechanical engineer, Jinseng Huang. He was professor at mechanical engineer at UNL.
Okay.
And so we collaborate.
And that's about solar panels, right?
Solar panel, yeah. So it's a hot field.
Totally hot.
Yeah, very hot. And so he kind of brought me into the field. I didn't study that, you know, but he said that this is a hot field. We have some theoretical, you know, problems want to resolve, and so I came up and helped him. So that made to a Nature Energy.
And the second highest paper here has a title that doesn't really tell you what it is: a droplet-based electricity generator with high instantaneous power density.
This one is also very interesting. Actually, I can give you later a link. You know, UNL also has a feature story on that. So this one is on how to harness so you have this rain, but Nebraska doesn't have rain a lot. Doesn't have rain, you know, but it's in a rainforest place. They have a lot of rain, and then once you have rain and the heat, so once they hit the surface, and the spread. They want to harness that energy and turn that into electricity. This is a technique developed by my colleague at City University. So that's why I collaborated with him, and that's why he brought me sort of to the City University of Nebraska. He was at City University 6 years ago, but he found me on the web. Actually, I didn't know him in maybe 2017-ish, because we study a lot of water, ice. And so he thought maybe I'm the guy who can help solve some theoretical problems for them. So he's also highly collaborating international. I didn't know him, but he find me in the conference and say whether we want to collaborate. So this kind of international collaboration was really fruitful.
But that one was published in 2020, and it's got over 1,200 citations already. That's 200 a year.
Yeah. That one is hot.
Clearly, this is grabbing people's attention.
Yeah, because the energy conversion. And so they thought about, actually the experiment did this kind of droplet during the raining. They can transfer the mechanical energy to the electricity, and the electricity can light the bulb, light bulb. So if you have a rain, then the light bulb is on. And then when the rain stops, the light bulb is off. So it shows this, water generated electricity. It was very fun. Yeah.
So on the ordered-iced nanotubes, I know that you came up with some practical uses for it, but why do you think that one's so popular? Why do people cite that one?
Oh, this one is certainly ice and water are very, I find water and ice are always got a lot of people's attention.
Okay.
But this one is the first one-dimensional ice predict. And people, there are about 20 three-dimensional ice in the world. And because hydrogen bonding is soft, they can adapt the environment so quickly. And so if you add pressure and temperature, and then they adapt, they change their structure. So that's why you have the rich ice structure, ranging, there are about 20, more than 20 now. And inside the Jupiter, the highest pressure, that's called ice 10, And normally we only see ice 1. So our idea at the time was how the water and ice hydrogen bond adapt the small world environment, highly confined environment. And so we studied Nebraska. It was our first try to see a confinement of two-dimensional.
Yeah. And
so the distance between two surfaces about less than a nanometer, and how water adapt to that kind of extreme environment. And when I gave this talk during my tenure promotion, I said, this the water can adapt, the hydrogen bond can adapt, like they find a way, nature find a way. I remember that's how I say. And then it's a new structure. It's Nebraska structure. Yeah. And one-dimensional is even imaginary because it's so small. It's one-dimensional small, and how water adapt that. And I showed you that structure. So maybe it's called ice rule. Maybe I have to quickly the ice rule. Every water molecule has 4 hydrogen bonding neighbors. Yeah, it's a jargon. Sorry, it's a chemistry jargon. But it's neighbor. Why? Because the jargon said the water has 2 protons, called the hydrogen proton, but also has 2 lone pair, electron lone pair. Yeah. So they prefer, all these are connected. One is donor, one acceptor, like a marriage. Donor acceptor like a marriage. Okay, so they have there are 4 marriage.
Complementary.
The way the ice rule. And this one-dimensional ice satisfy this ice rule. So that's how we predicted. And so that caught a lot of attention because the intriguing. And when we changed the diameter a little bit, it changed from square to pentagon, and pentagon to heptagon, and heptagon to octagon. So it's but by changing like 0.2 or 3 angstrom, that little distance, the structure changed, adapt to from pentagon to hexagon. So we predict all these ices at the time in 2001, and 3 years later, all these ices were discovered worldwide. by Japan, Germany group, US group. So now it's called ICE 1, 2, 3, 4. One-dimensional ICE 1, 2, 3, 4.
Yeah. Nope. Really exciting.
Yeah, it was fun.
Very fun.
Yeah, that's my 8th year. So that earned my 21, earned my full professor. I got a full professor at 201 and promoted to chair professor Willa Cather in 202.
Okay.
So that was
very important to your story.
Yeah, those yeah. So I was 9 years after my entering UNL, I become chair professor.
I know, it's amazing. Such a fast rise.
Yeah. So because of these Nebraska ICE Nano. Yeah.
All right. So let us talk about curatorial activities, interacting with other scientists. I don't know if you edited any books or were leader in any societies.
Book I did. Yeah, I spent too much time on writing paper. But I reviewed. I wrote several review articles. That's like you can see that sort of like book chapter. So I had a book chapter. Yeah, to spend book. Maybe after I truly retired. Right now, I'm only retired from UNL. I'm an emeritus professor, but I'm still head of the department. Maybe when I truly retired, I have more time to think back. Then maybe I'll write a book. But right now, review article is kind of a good way to summarize my 10 years, 15 years, understanding of the field.
So when you were at UNL, you were funded by a number of agencies. Just tell us about some of those and how they changed over time.
Yeah, mostly by NSF. Yeah, my very first grant NSF was to Japan. It's called, so now these grants are no longer there. It's called Medium Visit of Japan. So I wrote a grant, and in the first year, so I went to UNL 93 and I got a grant 94 in the spring. So I've spent a month in Japan, in Kyoto University. So, and then that allowed me to recruit my very first postdoc, Koga, and he worked out that Nebraska ICE, and then now become a professor. So, and my second grant also in NSF study the water nucleation, and also they have, at the time they have something called additional grant for visiting a foreign country. And at the time I choose China, so they fund me to visit China. It's a university called University of Beijing, University of Chemical Technology. So they give me the visiting grant, and then they recruit my another postdoc. And so NSF support my most grant, but I also got the DoD like app score and the DOE, but I would say the university has this called you call it the Nebraska Initiative grant was very good. David Summer, the used called CMRA, now it's called NCMA. Yeah. So they also provide some matching grant, really help me a lot. So I got the NSF grant. They give me 5 or 10% matching, so allow me to use that to hire postdocs. Yeah. So
most of it was then salary, but then the computers, do they cost a lot of money?
Yeah.
Did you get instrument grants to buy computers?
Yes. One of them, the first one was the I got this. I wrote grant with John Stozowski. And he was into the silicon graphic machine. So we wrote a grant to NSF, something called the equipment grant. We got it, and John and me. So we got that grant, and we built a very good big medium level cluster in the department. Yes, that was 97. I remember. Yeah.
And that was for mostly visualization, right?
We bought two clusters, one for visualization, one for high performance computing.
Okay.
So John managed that graphic part because he wanted to see high resolution crystal structures, and I want to have speed. So we got 50-50 split on two clusters, big clusters. Yeah, that was very fast. That one, it made me maybe one of the fastest on campus.
Yeah.
So we were very successful to get a major grant, and I think a university also gives a match. Peel at the time was the chair, so give us a match. So we were very fortunate to get that equipment grant.
Amazing.
And later we also get a much bigger one for the prior fire. That's a NIS app score, NSF app score. That may be like $500,000-ish. Yeah, very big. So that's how I get Dave Swanson back. He was at Navy as a postdoc in the Naval Research Lab, and I gave him a call and see whether he would be interested.
Can you describe the how the computational energy measurements work for a layperson? Your students and postdocs, they have force fields, but how do you put molecules in a force field and then figure out how those molecules interact?
Oh, okay. Yeah. So it's so the molecule in the reality, they interact by Newton's law, right? Let's use classical one. If you play billiard ball, it's follow the Newton's law. And in computer, we turn this Newton's law into differential equation. This Newton's equation is a differential equation. F equal to ma, but the a is a double differential. It's a d square x dt square. So t means time. So it's a differential equation. And in computer, that's how to solve this differential equation in order to track, the two molecules, how they interact, how they collide. So it's a reflect of reality. The billiard ball, when you play the pool game, and but we play that game in the computer. So we solve that equation to describe two molecules collision. Now, if you have ice or water, you have tens, thousands of hundred. So the more of them, the more equation you need to solve, and the more powerful computer you need. So it's end up solving more and more equations. But the idea is you track, this Newton's law in computer. In reality, you only see in your eyes. When they collide, they will bump each other, right? When you play ball, if you are very good at, this pool game, you can aim, and then you aim an angle and then let it go to another way, right? Collide. And in computer, we don't aim, but we just follow their random collision and see how they involve, and let the nature, like the temperature, handle their collision.
So then what causes the metal atoms or the molecules to stick together in your computer modeling? I see. That one, you have to introduce something called attraction. Yeah. And you have to make it if they collide, and then they met you call it very strong attraction, or very deep. We call it the potential well. And then it's like maybe when you happen to run the field, and then there's a deep hole, and then you fell in the hole, and then in a sense you bond with the earth. You're trapped in that hole. You fall into that hole. Yeah, and it's hard to get out. That's kind of a knowledge of the whole molecule, because they stick together because they're trapped in the potential well. So water turns into a very complicated problem then, because it's three-dimensional. The shape of the interaction.
Hydrogen bonding. In computer we describe, we need to introduce charge, positive, negative charge. So it's Coulomb interaction. Still, it's follow the Newton's law, but so it's harder to solve. Yeah, when I was a graduate student, we don't have that big computer to model water. So at the time we studied argon, hardball. We call it hardball and argon. It's easier and to handle, and that's why after I become assistant professor, the computer become faster. PC came along, personal computer came along, and it's cheaper. My startup is not so high. My startup is 80,000. That's all Pure gave me. Yeah, that's all. 80K now. Right now, I know the startup for a chemistry professor is way above.
Yeah. 1.5 million, 2 million.
Yeah. But PC was, AC, XT, AC, those PC was priority for me to study water. Yeah.
Okay, so that sounds really exciting. And then my next one states that research is competitive and cooperative. So were there other people working in the field, and did they publish the same results at the same time? Or was there any sort of a controversy that arose because of two people publishing around the same time?
For me, I was lucky because, there's two-dimensional ice, one-dimensional ice, bucketball. I was the first one to publish them. So the way I kind of lead the field, and then that's why they have a lot of citation, because after we publish, a lot of people were intrigued by the result. They start entering the field. So certainly it's a good thing the citation people are interested. Then there's some kind of project follow-up, but maybe they will go ahead of you. I cannot handle them, but it's good in the sense because they cite me, they follow the field, and they made a new discovery along the line. Even though they may be ahead of me, but I'm happy because it's always go back to the root. So I'm okay with it. I'm okay with it. Yeah. If the bucket, those Gold 16 were discovered by someone else, and then I follow, then that's certainly. But if I already discovered it, but I didn't publish early enough, that would be a disappointing. But I didn't have too much of that. Okay. So I was about lucky in a sense. Maybe because theoretical work is less competition-wise, is less than the experiment, because experiment, when you made it, and then you need to make a pattern. Theoretical work have less pattern-driven. It's more like prediction. And once we predict those Nebraska ice, we're hoping to get attention of the experimental group to make it. So it's a different mentality, theoretical one.
And you do a lot of collaborations too, right?
Yeah. Because later and later, early time in SF, mostly single PI grant. Craig told me, in the good attempt, single PI grant was very popular. And then in the 90s and later, all kinds of collaborative grant become very popular.
Yeah.
And so that even AppScore, where AppScore stay, and that calls for a lot of collaboration. So that kind of funding driven, the people work together. And but I also feel fun to work with experimental people, because if they have something real problem, and if I can help them to resolve some of the theoretical issue, that's fun. And also benefit my students. A lot of my students, after training, they also become collaborative when they become faculty. Yes.
You're right. So let me ask you about this paper that I saw was retracted. Why was it retracted?
There is a correction paper published.
Oh, okay.
Yeah, because at the time we have a big data. We calculate maybe hundreds of systems. We use a low resolution criteria for a fast speed. And then later, when we use higher resolution, we find the correlation formula is different. So we published a follow-up paper, a brand new paper. It's called Revisit the Same Problem. So it's a correction paper published along the same day. Yeah.
So it's called a universal principle for a rational design of a single atom electrocatalyst.
And then the other paper is called the revisit of something generic principle of this. Yeah. It's a longer paper with different correlation. And
and is it as popular as this one was?
Yeah, it's also
this attracted 1450 citations. This was a big
but
number.
that one is maybe several hundred now.
Okay.
Yeah. It's they still wants to publish, but in a new paper rather than just correct a formula. I asked the editor, so they want to publish a new paper with this high resolution data.
And then let me ask you about, you got a couple patent applications while you were at the University of Nebraska. And here's one called mixed tin and germanium perovskites. Tell me about that one.
This one was remember this Professor Jin Song Han brought me the field of solar cell.
Okay. Yeah.
And so we and then because that solar cell material has lead at the time. So people thought about, can you make a perovskite without lead? And so we thought maybe in the periodic table, the lead, tin, and the germanium, silicon, they are in the same same column, right?
Same group, yeah.
So it's a purely imaginary theoretical one.
Okay.
And then we thought maybe if we made the a patent, and the later people could if they make successful. But it turns out lead still at the tail. Lead is still key important, and the tin and germanium they could make it, but the efficiency is much lower. Yeah. So lead has some kind, because some of the chemistry of lead make it very, 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 very efficient, high efficient.
The ionization potential, or what is it about lead? Just what is the issue about lead? Why is it so good for perovskites? Is it the ionic state?
It's still kind of frontier research why lead is so good. Yeah, it's because this one has a lot of elements in there. So it's hard to point a finger to one reason. But it's a combination of a lot of, but lead is very heavy, right? It has a strong relativistic effect. They also called something called strong coupling, strong coupling with the spin electron coupling. So it's a lot of jargon, but it's a magic. Sometimes it's magic elements that make it work.
Yeah, absolutely.
Yeah.
All right, well, let's move on to other career activities. And so I want to know about the societies that you were a member of, and then what conferences you attended regularly, and was there ever a meeting that was especially memorable?
ACS, I went there quite regularly, and also early time, the Gordon Conference, I also, on the liquid, Gordon liquid. But certainly Gordon was very, very interesting, because a lot of people sitting in the room and then just debate something rigorously. So that gave me a very different perspective. ACS, everybody gave a talk for 25 minutes and ask a few questions, and then next, right? But Gordon is different. You're forced to be in the room, and then people give a talk. And then the next, maybe 1 hour or something, you can discuss. So very rigorous. So I was young, I didn't speak, but I listened how they, think, how they debate. So that's give me, you can see some of the famous people, National Academy member, they disagree, but then how they think from this way, that way. So that's really helpful. And it's make my eye open, I would say. Yeah.
Did you ever take a sabbatical?
Yeah. The first one was 2000. Okay. Yeah. Was to Hong Kong. So to Hong Kong University. That's why I had a good impression of Hong Kong. So I spent about 4 months in Hong Kong University. And so and later when they find me for this job, I didn't apply this head. Somehow they find my name and ask me if I work in the pool, and I thought I was in Hong Kong. I had a good impression, so I said I can be in the pool and the short list.
Yeah. So then service at the University of Nebraska. What service contributions do you remember the most in the department, the university, the community, and nationally?
Yeah. If I can share with you some.
Sure. Yep.
Yeah. The university one, I'm department one, I really very proud of is, let's see if I can share this one. Let's see. Can you see but I want to see you there. How do I there is a faculty award, but somehow it's blocked. Faculty award, like where's faculty award? Oh, this is Nebraska department. I want to go to the department.
Chemistry department?
Chemistry department, yeah. Maybe sorry, let me get that. So that shows my, here, I got it. Okay, now I can just share again. Yeah. And yeah. You can see this?
Yeah.
Yeah. So this is department website on faculty award. And I have been the award committee chair for 15 years.
Right.
Yeah. And I can see, if you look at my contribution, I can start from, you can see college OCAR awards. So you will start to interview these people, I guess, right? This is OCAR.
Yeah.
OCAR, right? You can see my cursor, right? 202.
Yeah.
And from 208 then on to 2018, all these 1, 2, 3, 4, 5, 6, 7, 8 people, I nominated them.
Oh, okay.
All of them. Start from Jim Tackis, Dave Hage, Dave Berkowitz, Pat, Andre, Liang Cheng, Robert, Bob, Gentile. Yeah. Alex was nominated by Dave Hage. He took the chair position later. And all these, Wheeler Cather.
Yeah.
I was at 202, and since then, all these, Jim, Marjorie, Dave, Pat, Andre, Dave Berkowitz, those by me. And if you look at the university professor, these, I was at 206, right? And Jim Tackis, Dave Hage, by me. And then OCAR, the next one, you look at the OCAR. It was 2010, and the next one with Dave Hage. Oh, you saw give you a list of OCAR, right?
Yeah.
History. The very first one is Norma, and then Napa, Ruben, Pill, me, and Dave. Yeah.
So I've already interviewed Ruben, Pill, and Dave. Here's my last one.
Oh, Dave Hage, you mean?
I already interviewed him, yeah.
Oh, Dave Hage? Oh, okay. Then the next one is go down the college OCAR. Yeah. Right? Yeah. So you have Jim, did you interview the Dave Berkowitz?
I did interview Dave, yeah.
Oh, you did? Okay. Then Pat, Andre, Liang Cheng, Bob, Gentile, and Alex. Yeah. So these are the OCAR. Yeah. College, they call it the college OCAR.
Yeah.
Right. So this is my biggest. I'm very proud. My successful rate was pretty high at the time.
Yeah.
So 1 year, you can see 14, 15, 16, 17, 19, one at 1 year.
Pretty good.
Yeah, back and back. Yeah. So that's my service for the department. At the university level, I was serving on Dave Steinmeier's committee, advisory committee for the material research. And university level, I remember some dean search and vice chancellor or senior vice chancellor research. I was on the committee for those. Yeah.
So then how about teaching? What courses did you teach more often than other ones? And what were your thoughts about teaching those?
Yeah, teaching those was fine. In Hong Kong here, it's one course per semester. Same. Yeah. Same. And yeah, we use American system here. So everything. So it's not from Nebraska to Hong Kong. It's a pretty straightforward. And you can see this is the textbook I used. You cannot see it. It's a physical chemistry by G. McCurry. It's like 1 kilogram or 2.
Wow.
yeah. It's 482, 481. Yeah, very heavy. Okay. So I've been teaching this for 20-ish years.
Oh yeah.
Yeah. It's a good one. It's a good book. And I don't know whether the PChem still use that, but at the time, Marjorie Langell, me, and Harbison, Jerry Harbison, Craig Eckhart, we all use this book. Yeah. So students were good. I mean, the students, undergrad students, if they are interested in physical chemistry, most of them are pretty good. A lot of chemical engineer students are very good. Yeah.
Okay, so let's move on to your youth. Tell us about what it was like to be you when you were a child.
So I was, if you know the history, Cultural Revolution, so I was born during that time. Yeah. You heard about culture. So that was a tougher time at the time until 77. Yeah. You heard about the leader called Deng Xiaoping? Yeah. So he promoted this open to the West, and then China start to recruit, allow students to take exam to go to the college. Yeah. During Cultural Revolution, there's no national exam for college. So I was lucky when I was in high school that open policy started, and then we can take exam to enter college. So I was get a pretty good score to enter, this Peking University. You call it Beijing, but it's also called Peking University, which is like Harvard of China. They were in the top 2 university in China.
Absolutely, absolutely.
Yeah. And so that's allowed me to. So at the 3rd year, they had a program to organized by this Nobel Prize winner, T.D. Lee. He was in Columbia University in New York. So he has this national exam program for physics students. So top 100 students in China can go to US. So I was lucky to make to the top 100 through national exam. So I went to Ohio State. So I was lucky in my middle high school age. I had this big transition from Cultural Revolution to open. They called open to the West. Open the door to the West. So that's I was lucky. If I were 5 or 10 years late, then it's hard to imagine where. So it's sometimes the environment, the big environment is pretty important. Yeah.
So what got you interested in science?
I was when I was in high school, middle school, I was pretty good at math, and very good at physics and math. Yeah, but also because my father was a professor in the university.
Okay.
He was in the physics. So he also want me to be in this area. So
okay.
So that's their family influence. But also I was on the math competition team in the high school. Yeah.
Oh, okay.
So once I'm pretty good, and then you take national exam, and it's all score, the top score one go to number one, number two, and its competition is high, and it's all score. It's like the sports. Yeah, the score is score wise, and then you go down the yeah.
So it must have been a very good high school.
Yeah. I was at this called Affiliate High School of Beijing University. Yeah. So it's also competition to enter into that class. And once you enter that class, it's like, in the US you also have this kind of school, prestige school in New York, and then once you get in there, it's easier to get Ivy League. So it's the same, very similar system. Yeah.
Preparatory school.
Yeah. Boarding schools. Yeah, something like that. In Hong Kong also, it's a very expensive international school or some. You pay, and then they have called the Band A, Band B, Band C. A allow you to go to potentially Ivy League or Cambridge, Oxford. Yeah.
So when you were an undergraduate at University of Beijing and you were majoring in physics, did you do any undergraduate research, or how was it structured there?
Yeah, the fourth year you have to find a professor to work on a project and write some kind of undergraduate thesis. Yeah, you're successful in using that.
Yeah,
you got a grant. I remember now. I remember you. Yeah, it's something along that line. Yeah, so I spent that number 4 year whole semester. We don't have much class, so we mostly spend time in the lab to do the research. Yeah, and I'm also preparing some kind of exam, national exam to US. Yeah.
Well, what research project did you do?
Oh, that one was something. It's on condensed matter physics, because I was so you can call it materials physics.
Yeah.
So I was study some magnetic material, very popular in UNL, Dave Sedgmeyer's field, magnetic materials. That was so. I kind of knew Dave's name when I was student. Dave was very famous in the field of magnetic materials.
But it was all physical work. It was not computational.
Correct. But I learned I wasn't good at the experiment. So when I was in Ohio State, I selected a theoretical professor. Yeah. Because I like thinking, I like math, I like computer. Yeah. So my PhD was in theoretical physics and more chemical and also chemical physics. Yeah.
And that was when the computational tools were getting much better, right?
Yeah. During my Ohio State, there's no PC, so people use this giant machine called, mainframe.
Yeah.
And so I have to walk, 100 or 200 meters to get data from a big building, a bunch of paper. Yeah. And but it's already better. I at least I can type thing on the monitor to send the job. In the old days, some people use some kind of
cards.
Yeah, some kind of plastic something, I don't know, to get the data. So I was lucky, but I still nobody the whole university only have one or two computer. It's not affordable. But near the 88 PC Apple comes up. Apple II and the PC XT. It's Asian, but but it's affordable. But it's still maybe at the time $5,000, $10,000.
Yeah.
But it's affordable rather than million or 10 million.
Yeah.
Yeah. So that's and by the time I did two postdoc, Chicago, UCLA, and the price went down, computer get faster. Some workstation come up called Sun Workstation, Silicon Graphics.
Yeah.
Those come up, and I was lucky. So it's lucky. If I weren't without those, I have to do paper and pencil work. More like a Gordon Gallup,
Yeah.
I have to use pen, and then but I was lucky.
He used the University of Nebraska's first computer back in 1960.
Oh, okay. Mainframe. I'm sure that's
it was huge.
Huge.
So what molecules or atoms did you study at Ohio State?
At Ohio State is it's because it's physics, it's material. They don't study material, they study the whole material. It's called in the alkali metal. Yeah. In physics called the simple metal because it doesn't have that. It has an easier electronic structure than the alkali metal. Sodium and potassium, those. So we study the liquid metal behavior, surface and surface tension. So that's my first project. I know that's my very first project to study surface tension of those metal because my advisor, a theoretical physics study, he got this money from NASA to study this metal surface behavior.
Then you did two postdocs. Tell us about Chicago.
Chicago, I transferred from physics to physical chemistry. So I went to physics, chemistry department and work with Professor David Oxby, and who is a theoretical chemist. And his field was the freezing of water at the time. Freezing of matter, mostly simple molecule like argon to start with. But his students started freezing of water, how to model this freezing behavior, and also nucleation. So I start to get exposed to the water ice problem in Chicago.
And then how long was that?
3 years.
3 years. Oh, I didn't know that.
Yeah, 3 years. Yeah, because I transferred the field from physics to chemistry, it takes longer time, and that's why after 4 years I can apply in Nebraska chemistry because enough training in physical chemistry. So I attend ACS meeting, all these, and to get into physical chemistry, and based on my condensed matter physics background.
How about UCLA? What did you do there?
That one also, it's Daniel Kivelson professor, and his field is also supercooled water, supercooled liquid. Yeah, and it's a very tough field. After UCLA, I didn't get into that field because it's very controversial. That's why I said in Gordon Conference, people debate about it because the glass transition is tough because glass has no odor. And then how do you describe this glass? It's really, a tough and could be very highly debatable issue. So I go back to Chicago work, order the material. Its odor is crystal. You see what you get it. So that those ice nanotube, Nebraska ice, these are ordered class, ordered crystal, and no controversy. Yeah, so it's good to find something so tough. You better not get into it as assistant professor. But now, lately, as a senior professor, now I start to get into it. So I had a paper, just published actually yesterday, along that line. Yeah,
real fun. So, how about your very first paper that you authored? Do you remember what that was?
Ohio State.
Ohio State.
Yeah, as a PhD. That's a surface tension of liquid metal. And
did you write the first draft, or how did it work?
No. I was I worked with I was the first year. I worked with a 4th year, 5th year student, So he wrote it, but he has project for me to work on. And so it's the professor divided project into small piece and give to me. That's my very first to learn it and work it out. And then so I was number 4, number 5 author in that.
Still very exciting, right?
Yeah, still very exciting. And then after that training, I start to have my very first author on liquid metals of extension. And the next paper, I was the first one. Only 2 authors, me and my advisor.
Oh, yeah. That's a good paper then.
Yeah. But it's the first one. Yeah, it's a good learning experience as a. So that's after. So at the time in the second year, because first year we always work on the courses and this qualifying exam.
Right.
It's tough. Those qualifying was tough.
So in retrospect, then, how much did your UNL research diverge from your graduate and postdoc research?
More like postdoc in Chicago work. So I turned into physical chemistry and studied the freezing problem, water freezing. So that become my main research until today. The study, except I study, freezing under nano environment, nanotube, Nebraska is and also in, all kinds of more complex environment. Yeah, instead of just glass of water in, that's straight.
What made you think of confined spaces?
Yeah, at the beginning, the reason was my computer was small. I cannot afford to study glass of water. And when you confine it in a small space, your number of molecule from 1,000 to 100.
Yeah.
So I cannot. My startup was a bit. I have only. I bought second-hand workstation.
I didn't know that.
So it's so I bought a couple of them. It's like, maybe 20% of the original price. So, but unfortunately, I learned how to manage those computer better. Yeah. So I bought a few of them. Used that ADK, and then hired a postdoc, and then I need to start. I need to publish something. The pressure pill.
Yeah.
We need to publish.
You need something.
So it's a compromise of speed and also new field. Away from my postdoc work.
All right, let's talk about the personal side here. Did you marry? I know you did. And then have children. And then how did they fit into this story of Ohio and Chicago and LA and Nebraska? Yeah.
We married at the last year of Ohio State.
Oh, okay.
And then so she came with me to Chicago, UCLA, and our kids. First kid, only one kid was born in '98. That's the year I got tenured.
Oh.
So talk about pressure, right?
But your wife was not a scientist, right?
She was a medical doctor in China, and then in US, she originally she had a job of working in the medical medical related place, the pathology place. So she screened some of the slides for cancer or something. So she worked on that for several years, and later she become associate director for Confucius Institute. At UNL. At the time, because there are many collaboration between UNL and Xi'an Jiao Tong University to China, and then they had almost 15 years very close collaboration between U.S. and China University. And later, and because the geopolitical issue, and that institute was gone.
Right. No, that was when the U.S. government wanted more collaboration with China.
Early time. Also, also because remember that they called the global engagement. The dean Joe Francisco, they encourage us to open the eyes to global engage. Yeah, those at the time the KPI.
Yeah.
But also in the university had for some reason they established this institute to have more cultural exchange. So at the time, my wife actually brought this president Harvey Perman, to China, visit the Xianjiao University, and they established this this kind of teaching Chinese class in the university. So she managed those teaching class. So that was a very fun time.
No, I didn't remember that she did that. So what do you do for entertainment or relaxation?
Well, football was watching football.
Watching football.
Football, because I learned watching football at Ohio State. I knew Big Buckeye was good, but not great. But then at the time, I heard about Oklahoma and Nebraska was like, very sooner, and the not Buckeye, the Big Red were kind of rivalry. So I was also lucky in '93. That's not the first championship in '94. So I see how people, witnessed from '93, '94 how Tom Osborne lead the first national champion, and then the next one and the next one. So that was dynasty. That's a great time. The last dynasty of Nebraska. 93. Remember 94? If you see the stadium, 94, 96, 97, I was there. I was there in 93. And I learned, oh my gosh, this kind of 90 champion is like yearly event, almost like I was, it's just so exciting. And so I start to analyze those games.
You did.
I did. I was because I'm a theoretician, and so I looked at, because at the time there are two poll. One is called the coach poll. One is called the press poll. So you only need the one poll to get national championship. So I was look at the data and see. Certainly, if you win all the way, but if you lose one, that one also, and see lose one, and how do you figure that out? So I was analyzing. So that's a really, really fun time. And later I got into watch some of the women's volleyball. That's really fun. But also I for the we had many faculty from China in the department. Like Liu Cheng. And we lead, and we often get together, watch football or the cook together. So and talk. So those are very light moment, and those the department really very good to hire some of the faculty from China.
Hong Kong.
And we were very close.
Absolutely.
And then later we have from Hong Kong. Two from Hong Kong, Barry and Rebecca. So that's why I have Hong Kong. They had some influence on the Hong Kong side.
All right. Well, thank you very much for talking to me today, and I really enjoyed listening to all your stories.
Oh, thank you, Mark.